Okay, let's get started. So today's speaker is Professor Aaron Roodman from SLAC National Accelerator Laboratory at Stanford University. Aaron is a case of a particle physicist converted to cosmology and astrophysics, which seems to be happening more and more over the past few years. He was an undergraduate at Caltech and a graduate student at Chicago, where he worked with Bruce Winstein, who many of you remember also worked in the CMB. Then was a postdoc at Fermilab and moved to SLAC, where he moved up through the faculty ranks. And he's now professor of particle astrophysics at SLAC and the previous chair of the department. Aaron, with his switch into cosmology, played a significant role on the dark energy camera experiment, and then on DAISY, and then more recently and most extensively on Rubin LSST. So where he was the leader of the camera effort in commissioning and is deputy director of the observatory as a whole. So today we'll hear about first results from Rubin. Many of you may know that the first light occurred in June, and the observatory is undergoing commissioning right now and is just about to start operations.
Good. Thanks, Steve. Okay, yeah, it is my pleasure to be here today and to tell you about the Rubin Observatory, the LSST Camera. It is the world's largest. Some of the early results, and then we'll talk some about our potential for the future. So, having worked on this project a long time, for many years, we showed images like these, CAD models of the telescope or camera. And of course, it's very gratifying that now I don't have to show those. I can show pictures of the telescope assembled in Chile, the camera, and these even are ones that are now a couple years old, where before the two were mated together. So our mantra is that we are going to take a color movie of the sky. We're going to do an optical near-infrared survey of the entire southern hemisphere to a depth close or beyond 27th magnitude in 6 filters, fast enough to see every part of the sky over 800 times. And that unique and powerful sample of images will enable a wide range of different scientific topics. So I'm going to tell you a little bit about the telescope and instrument, show you some of the fantastic videos we produced from our first set of images. And so if you've seen those before, I'm sorry, I'm going to show them again. And then talk about some of our early results. And then switch gears to talk a little bit about what we see as our potential for cosmological study with this image sample. But before doing any of that, I do want to acknowledge our namesake. So originally, we were the Large Synoptic Survey Telescope, and we changed our name to the Vera C. Rubin Observatory and kept the acronym LSST, but renamed it Legacy Survey of Space and Time. So we didn't have to change all of our logos and websites and such. But it is actually a very nice aspect of the observatory that were named in honor of Vera Rubin. So I assume people have heard of her and know that she, among her contributions were the first really compelling evidence for dark matter, looking at gas around galaxies. So with that, I'm going to launch in and say a little bit more about what our goals are in the survey. So we want to image the entire sky quickly. So with the capability of seeing every direction available to us from our mountaintop in Chile in just 3 or 4 nights. Those would be deep images with 5 sigma source detection limits at these levels in our 6 filter bands. So those are interference filters that pick out a portion of the visible to near infrared spectrum. In total, we would see over 18,000 square degrees of the southern hemisphere sky, and as I said, see them over 800 times in 10 years. There is also, in addition to this wide survey, there is a secondary survey looking at 6 particular fields, deep drilling fields we call them, that we would be able to observe many more times. Either 10,000 in one of the fields we would see 20,000 times over that 10 years. We estimate in total we'll observe 20 billion galaxies and 17 billion stars in the Milky Way. We estimate 6 million solar system objects, so mostly asteroids. Seeing them almost 1,000 times gives us a database with almost 40 trillion rows. So each image, each object seen in each particular image. So that's an exascale database, not small. With that, we would study dark energy and dark matter and the expansion of the universe. We'd catalog the Milky Way, explore the transient sky, which I will say more about. And interestingly, all of our image data catalogs are public. There's no proprietary period. So for anyone with data rights in the US or our select international partners, once the data is available, it's available to everyone. Now, what about the transient sky? Every image we take will be sent in real time back to our data center. It happens to be at SLAC. And the analyzed quickly, calibrated, and reduced, and compared against previous images taken in that direction. And so any object that's observed to change, so asteroids, moving objects, any new objects, supernova, or any of a host of different transient objects, or just variable objects, from AGNs to variable stars, will be flagged. And a message, so our jargon is an alert, will be generated. We estimate between 1 and 10 million of those will be generated per night, and covering a huge range of different phenomenon. And those actually are sent to secondary data processing sites, brokers they're called, where people can contribute algorithms, filtering algorithms to select out the images or the alerts of those sorts that they're interested in. So in a nutshell, that's our program of imaging and alerts. Now, so that's the introduction. So next I'm going to change gears and talk a little about what we built. So about the telescope and the camera. Maybe a little bit more on the camera since that's what I've been focusing on the last 15 years. So the first design criteria for the entire observatory is survey speed. So we wanted to maximize the étendue within the, what we thought was possible and feasible with the resources we were able to marshal. So the étendue is the product of the mirror area, the primary mirror area, and the field of view. And the total is this number, almost 320 meters squared, degrees squared. The primary is 8.4 meters diameter. As you'll see in a sec, it's actually an annulus. And the field of view is 3.5 degrees across. And this is an old picture showing kind of a life-size diagram of the field of view with what the full moon would look like interposed on it. Although we have learned already that trying to image the full moon is a bad idea. So next, the telescope design. So with this large field of view, we made the choice to go with a 3-mirror design. So the typical large telescopes are 2-mirror systems. The advantage of the 3rd mirror is that you can correct astigmatism over the wide field of view. And in other systems, you have to do that correction elsewhere, often in a corrector optics. But in our case, with 3 mirrors, you can do that correction with reflective optics. The innovative thing, and you saw it on the previous picture, is that the primary, so the 1st mirror, and the tertiary, the 3rd mirror, combine on a single substrate with different radius of curvature. And that has not been attempted, certainly at this scale, before. So that has worked nicely. The other aspect of the optical design is that it's an extremely fast system. So it's an f1.23 system. So if you're familiar with regular photography, you know that if you want to see a wide field of view, you go to a fast system that has different constraints that it produces. And in particular, in cameras, you can get a nice narrow depth of field. In our case, we have a very narrow depth of focus as a result, but it gives you the big field of view. It has another advantage, which is it gives you, especially with this 3-mirror design that is nicely folded, it gives you a very squat design. So the entire telescope is only a little bit longer than it is wide. And that's good because for survey speed, we want to be able to slew from one part of the sky to another quickly, obviously to avoid time off the sky with the shutter closed. And to do that, a squat design is going to be better in terms of being able to return to the stability you need for each image. So the rough level, the required, what we designed to was to be able to slew kind of one quantum of the field of view, so call it 4 degrees in just 5 seconds, and become stable enough to start the next image just 5 seconds later. We are close to, not exactly, but we are close to that level, which is very fast for a large telescope. Okay, so how about the camera? So to match the field of view, we are pushed to an enormous camera with a giant focal plane to cover that field of view. For ground-based imaging, you want to oversample the point spread function. And what we've aimed for is delivered image quality under 0.8 arc seconds. Let's call it 0.75 arc seconds. That's full width, half max. That's sort of the typical measure of image quality. And we want to make sure we sample that with more than 2 pixels across. Occasionally, we will do better than that. I think our system is capable of 0.5 arc seconds ultimately. So a choice of 0.2 arc second pixels is a good one. It'll be oversampled, and that's a reasonable choice overall. The pixel size, 10 micron, is very typical. 10, 15, or 20 micron pixels are typical in CCDs. We chose 10 micron pixels, and that gives you 3.2 billion pixels to cover the entire focal plane. So and you're just driven to that by the size of the field of view. So that sets the size for the entire instrument. So it's roughly 64 centimeters by 64 centimeters. So that is truly enormous. Next, we want to see the whole sky quickly. So we want to get images in every direction in 3 or 4 nights. And the design was to do that in pairs of 15-second exposures. So 2 back-to-back 15-second exposures. It turns out we've now decided to just go with a single 30-second exposure. That's a detail. But 30 seconds gives us lets us see the dim objects we're interested in. That's the magnitude level that I already talked about. And putting that together with a number of images that you would want to take in a night, and to maintain good efficiency, so not so much time wasted reading out the focal plane, we designed for 2-second readout. So that's pretty fast. And to get to that level in 16 megapixel CCDs, we felt we needed to multiplex by a factor of 16. So our CCDs have 16 separate channels. And for 2-second readout, that goes to 0.5 megahertz, and that's doable given the noise level that we wanted to achieve, which is sort of 5 or 6 electron read noise. 16-channel CCDs definitely took a significant development by the 2 companies that we contracted with to build these custom devices. Typical CCDs have 2 readouts, so 2 amplifiers. There are some with 4 in the corners. Having 16 actually was a significant construction challenge and took an extended effort by our CCD vendors. But they did achieve what we needed in the end. Now, given that, we have 16-channel CCDs to cover the focal plane. We have 201 total sensors. 189 are used for the images. The other 12 are used for wavefront or guiding. But taking those numbers, we've got over 3,000 channels. And it looked like bringing out 3,000 analog signals out of our vacuum vessel really looked daunting. It's too many, difficult kind of in every direction. So the other critical decision was to put our electronics inside the cryostat. And that has the advantage of then you're digitizing very close to where the signal comes out of the CCD that has good properties for noise or crosstalk, but it is a significant complication to have that much electronics and cabling inside the vacuum vessel. But that's what we did, and we have achieved a system that works well in those conditions. We worked hard to minimize the amount of the focal plane that wasn't used. It's precious real estate. And lastly, and connecting to the other thing I mentioned about the telescope, with a very narrow depth of focus, we needed to maintain this very large, highly multiplexed focal plane to a high degree of flatness. Because if it had waves, or the CCDs individually had waves, that would give you parts in focus and parts out of focus. So our spec, I talked too long on this slide, I guess. Our spec was just 5 microns RMS, and we achieved 4. So with that, let's look at some of the pieces. So the top shows the primary tertiary mirror. This is at an early stage when it was still being polished and figured. I like this picture because you can easily see the inside part, that's the tertiary mirror, and the outside annulus, which is the primary. And the very big difference in the radius of curvature between them. The bottom shows the large, it's 3.4 meter secondary mirror, coated. And then if we want to look at the other optics, on the top left is the first refractive optics for the camera. And then underneath is the second. So it's actually a 3-lens system. The third in the upper right also serves as the vacuum window. The filters, which are very large as well, 80 centimeters across, here they are all sitting happily in their box. So, okay. So next, I'll show you a couple videos. It makes it a little bit easier to sort of get the scale of it and the sense of the whole observatory, seeing it move. So let's see. So this is a short video showing the telescope moving. In this video, we're actually moving only at a fraction of the speed that the telescope mount is capable of moving. We have tested at full speed before we installed the mirrors. With the mirrors on, we're gradually increasing the speed, approaching that sort of the design level. So there's still work to be done in reaching that level in terms of the control of the actuators that are supporting the mirrors under the load of gravity. But if you haven't seen a big telescope move before, already this is pretty fast. The full speed is really unbelievably fast. You have to trust me on that, I guess. You can see here the reflection pattern is actually kind of complicated. With 3 mirrors, you have to pay attention to what you're looking at. You can actually, this is actually a reflection of one of the filters in place as seen reflected back and forth once. And depending on where you're looking at, you're either looking directly at the tertiary or at the primary here. Okay, so now a little bit about the camera and its assembly. So on the left are a couple of the pieces of the focal plane. So let's go back here. So this is one of the 2 kinds of CCDs we have. They're assembled on a 9 CCD subassembly, and that's shown in full here being installed. And this is in many ways the heart of the camera. It's an integrated package, very highly integrated package, which is both an advantage and, shall we say, a challenge to both assemble and to test and install. You can see at the bottom are the CCDs, and then here are the readout electronics boards. There are 3 boards, each supporting 3 of the CCDs. It's also a thermal package. You can see some of the copper straps here. The CCDs are at minus 100 C, the electronics roughly minus 20 to minus 40. And so those are all very tightly integrated together. On the right, I mentioned that we worked hard to minimize the unused real estate in the focal plane. This is the nicest way of showing that. You can see one of these units already installed and the neighboring one coming nearby. There's only 0.5 millimeter between them. One of my colleagues liked to refer to this as parking a Maserati with about an inch of clearance between two other Maseratis, so, which is about right. And then here we're installing the very last of these units, and you can kind of see in reflection the full focal plane. So, but you get a better sense. I have a time lapse that shows starting in 2019. So at that point, of course, we already were deep into construction in the individual components of the camera. But at this point, we're assembling pieces, and it gives you a sense of how that looked. So here we're inserting the individual 9 CCD subassemblies. Kind of took a day each over a period of a few months. We're getting ready to assemble the kind of the front cylinder of the camera that holds the optics, the shutter, the filter exchange system. Here we're assembling the back side with all the support electronics, refrigeration equipment, vacuum equipment, et cetera. Now we're ready to take the finished cryostat out, rotate it, and assemble the back guts to it. Now with that assembled, and you can see the years go by, we're attaching it to the main front cylinder that holds all the other equipment, installing it in our test and assembly jig. Now we're attaching the front 2 lenses, and we are done. Now we're getting ready to take it out. Now we're 2024, wrap it up, put it in a box. We chartered a 747 to ship the camera. 2 of our engineers got to fly with it. And here is up the mountain. There's the observatory. Take it out. 6 months passed. Now we're ready. Take it. The camera goes in the inner aperture, in the hole of the secondary mirror, about a couple centimeters on each side. Watching it slowly. This only took a day, and then we're removing the lens cap, 5.5-foot lens cap, and it is ready to go. And that was mid-March, and we got our first images in mid-April. Okay. Goes fast if you look at it this way. So, all right. So as I say, so that was where we stood in April, and we started observing with the telescope as a whole. And the first thing we did, or one of the first things we did, was to conduct a short image campaign, both to assess where we stood in every component. So how well is the camera working? How well is the telescope working? The auto focus and auto alignment system, active optics. What's the performance of all of our image reduction pipelines? And then to put those images together. And I will say, of course, there was some aspect that was public facing. We wanted to announce that we had started, and so to have images put together in a way that we could show them to the public. So that's what we did over the course of about a week. And what I'll show you is focused, actually I'll show you mostly things from the first field. So one field was centered around M49. It's also in the ecliptic, so it's a good place to see asteroids. We took almost 1,200 images over just parts of 7 nights. We decided to use just 4 of the filters. One detail is our filter system only holds 5 of the 6 filters. There's not room to hold all 6. They're too big, and because of the constraints of how we have to move them in and out, we only have 5. So but we decided to actually just use 4. The total is only 10.5 hours of time, so it's actually just comparable to little over 1 night of images once we're really fully operating. And we covered 24 square degrees. So the field of view is 10 square degrees, so this is kind of 2.5 fields of view. I'm told it summed up at 3.5 trillion pixels total processed. So it's a reasonable amount of data, even though this is just a small part of the sky. We looked at a second field, which is the one shown here. This is the Trifid and Lagoon Nebula. Over 600 images, again, those 4 bands, a little bit smaller region on the sky, 13 square degrees. You can see it looks awfully nice. And if you want to see it yourself, you can do it on any web browser. If you go to skyviewer.app, and you can pinch and zoom going in and out of these images to one's heart's content. They look good. Okay. So here's a still from the M49 image. And to really appreciate it, it helps to zoom in and out. So here's the video we made. Oh, you can even hear the sound that does that. So I think certainly this does look kind of like what we expected these images to look like. If you look at deep observations with other telescopes, this is what we expect. I would say the thing that I found most amazing personally is that there's really no part of the sky that's empty. And that if you zoom in to any patch and zoom in enough, there are loads of galaxies everywhere, which I guess I knew is true, but seeing it in this way is awfully nice. And when we zoom out, you can see that's one field of view interposed on this swath of the sky. So at 24 square degrees, it's 1/800th or so of the total 18,000 square degrees that we expect to see. So actually just a tiny, tiny part of the sky. But I think this really shows the potential we have, for discovery, given the quality and depth of these images. Now, the other aspect I mentioned is the transient or time domain aspect of Rubin Observatory, where, as I said, for every image, we're going to compare it to previous images. So we did that as well with this sample, and because it was on the ecliptic, we expected to see plenty of asteroids. So the other video shows that. So here you can see a couple asteroids with multiple images. Again, it's just 7 nights, and most of it is actually just in the first 4. But as we zoom out and focus in on different little pieces of the sky, we see lots of asteroids. And this is actually the ones that are new. There was another couple thousand asteroids we saw that were already known. So after 7 nights, we see over 2,000. And of course, we're just looking at one direction in the sky. And so mapped onto the solar system, we're just really looking at a slice, just a small slice in one direction. But of course, over each year and over the 10-year survey, we will be able to completely map out this aspect of the solar system. So as I said, so now I'll change directions a little. So that's kind of the, some sense, the introduction. But I'll talk a little about some of the early returns, some of the early things that people in the community, people who are part of Rubin have been doing with our initial data samples. And as I mentioned, we usually talk about it falling into these 4 areas. You can see these are the things that we're expecting to do. Obviously, given an image sample like this, there's a lot of kind of known scientific topics to cover. One of the things I'm looking forward to is finding things that don't fall into any one of these categories, or at least so cleanly. And I do expect eventually we'll have plenty of kind of new investigation, new studies that these images will enable. But the things we're counting on, of course, are to study dark energy and dark matter with the huge sample of galaxies, as well as the transient objects we'll see. Study the Milky Way. I'll show just one early paper in that direction, some results from one early paper. You've already seen a bit of the solar system and a bit more about the changing sky. Okay, so the first thing I could talk more about, and this is actually Rubin's first science paper, is the observation of 3I Atlas. So probably know that this alien spaceship has now been seen, and So this is the third interstellar object observed. It was discovered by ATLAS. This is the Asteroid Terrestrial Impact Telescope on July 1st. But once that was announced, we went back, and it just so happens we had taken quite a few images in that direction. And it was in our images from about 10 days earlier. So if we had been in operation, we certainly would have seen it first. Right? It's actually a fairly bright object, so easy for us to see. So let's see. I think this is also a video. Yeah, there it is. In the images, in the middle, you can see the many individual observations of this object. And then as a function of time, we have a flux measure. And then it was compared in extent against stars from the same images. And you can see here it actually appears a little bit bigger than the stars. So it's not, we have evidence already it's not a point object. And I guess since then it's developed a tail, and lots of other telescopes have taken a look at it. But what this really demonstrates, I think, is a piece of our potential for, another piece of our potential for studying the transient universe. And in this, for objects of this sort, well, there are 3 seen in about a decade. This one is actually fairly bright, so it'd be easy, easy for us to see, easy for a small telescope to see. The distribution in size obviously isn't quite known with just 3 objects. The estimates cover a lot of territory, between 5 and 50 more such objects. So at 50, we would actually see a lot of these. And so it's an interesting other direction for studying solar system or other nearby solar systems. Okay, next, I didn't mention this yet, but in addition to the wide field program, so 18,000 square degrees, and the deep drilling field, so these fields we'll see many more times, there's a third aspect to our survey, which is a target of opportunity program. So we will devote 3% of our time to TOOs, and in particular ones that are, so that's cases where we'll stop our regular surveying, slew the telescope based on an observation from another instrument, and spend time scanning in the expected area of that signal. Those could be gravitational wave observations, so where of course we'd be pretty interested to see another neutron star in spiral, or really any kind of electromagnetic counterpart to a gravitational wave event. High energy neutrinos from IceCube, perhaps observations from the Water-Cherenkov Super K detector in Japan, things of that ilk. And of course, with a 10 square degree field of view, even given a large target area to look at, so in this case, this example where we did a target of opportunity imaging campaign on this particular gravitational wave event, this is sort of a test, it had a footprint, call it 30-ish square degrees, and so with our large field of view and the fact that we can slew rapidly and take images rapidly, we're a perfect instrument to follow up and search for counterparts to gravitational wave events. So that's what we did here. So the images we took are shown here. And there are from the Dark Energy Camera, DES, there were some candidates. We took a look at those as well. It was a chance to exercise our difference imaging pipeline, where you take, for each image, you compare against a template. In this case, we didn't actually have a template because we hadn't looked in this direction before. So we borrowed our friends over at Decam's images to use as our template, and then look at the residual. So in this case, this is a fairly bright supernova. So Decam also saw it. Here's our version. And this is a good example, though, of giving us a chance to really exercise the image pipelines to show that we got kind of what we expected. And actually, since then, this was done, I think, in July. We've also started to exercise the difference imaging pipeline on other images that we've taken as part of commissioning. So I don't actually have anything more to show you on that, But we are excited that we should start exercising that part of the observing campaign later this year. And so this was kind of a first example of that. Okay, so the next example is are going to come from a data set that doesn't come from the full camera, but comes from the commissioning camera. So last year, we took observations for 2 months with a small camera, so 144 megapixels, so for us that's small, with just 9 CCDs, but it's the same hardware as in the main camera, and gave us a chance to commission the telescope before the camera was ready, the full camera was ready. So we did imaging in these 7 fields. They're shown here, and several of them are fields that have had a lot of study from other instruments. So one from Euclid, one from Chandra, as well as ones that give us a range of different conditions, so useful for commissioning. The bottom plot shows kind of the sum depth in each one of these fields, and in particular, this one, the extended Chandra D field south, is quite deep. So it's not quite as sensitive as the full 10-year survey. It's kind of at the 5 or 6 year level. But already that's a great sample for us to study, to commission the telescope. And this data has now become public, and so gives our science community a chance, a taste of the kind of data that will be coming from Rubin. So just to show 2 different results from that. So this is a paper that's in prep that's looking at the structure of the Milky Way halo. And in particular, it's looking at the location of blue main sequence stars. And so the plot, so the top are, so it's magnitude and color for 3 of our fields with Rubin, and comparing it to simulation and a survey already done with DECAM, so it's called DES or DELVE. And what's interesting is that the simulations predicted this whole population of blue stars that is not observed. So it hadn't been observed in DES, but that was a shallower survey. And kind of the expectation was that these things in dimmer stars, which now with Rubin's extra capability we see are actually not present. So it shows that our models of the Milky Way in this one particular kind of star are not right, and that there's a real deficit of these particular stars. But we can, for the stars that are seen of this sort, we can map out where they are. So this is a plot in cylindrical coordinates showing along these 3 different line of sights it's actually a scatter plot. So it shows individual stars as a function of position in the Milky Way. But since it's only in 3 small directions, we're only probing these 3 pencil beams. So the potential, of course, is that with even 1 year of the survey, we'll cover the entire sky, so all southern hemisphere directions, and can really map out a huge portion of the Milky Way. Now, some of that has been done with the Gaia satellite, but Gaia only goes to about 20th magnitude. And so since we'll go to 24th magnitude in a single visit, a single image, and deeper than that summed, we'll be able to study a part of the Milky Way that Gaia has not been able to reach. So the combination will really map out a huge portion of our own galaxy. The other thing I can show you is some early work done in weak lensing. So this is some preliminary results and plots shown by Anja van der Linden at that come from the Dark Energy Science Collaboration, which is a big group that I'm part of that is aiming to use Rubin data to study dark energy. And so I think there's not anything that's really scientifically novel here, but the group was, at the same time happy to get their hands on a sample that's representative of what Rubin data will look like as a precursor to what's to come. So it so happens one of these fields had an Abell galaxy cluster that had really not been studied previously, A360. You can kind of see it here with all these reddish galaxies. And then this is the weak lensing signal. So this is a sign of the bending of the light from galaxies that are behind the cluster from the gravitational potential of the mostly dark matter that makes up the cluster. And of course, this sort of study is going to be a critical and really fruitful part of the science program from Rubin. And so this is sort of a first salvo. So this shows the lensing signal. These are mass maps. So these are taking the signal from the shape of galaxies and inverting that to give you an inference to the distribution of mass between us and those distant galaxies. And the E mode shows the expected signal, and so that's the lump of matter, mostly dark matter, that corresponds to this galaxy. The B mode, you don't expect any signal. That's the null channel, and you don't see much there. So that's nice. It's nice to see that, and it already shows a reasonable control of our analysis of galaxies, our analysis of the point spread function, some of the other predicates that you need to do this sort of analysis. Okay, so now, finally, I want to change directions yet again and talk about our potential, and in particular, our potential in the part of the science program I'm personally most interested in, which is the study of dark energy. And so, in case people don't follow this field super closely, just as introduction, I went back to one of my old talks from about 5 years ago and pulled out one of the slides that showed the state of the art in measuring the expansion of the universe with supernova. And the plots are actually from 2018. It was a talk I gave in 2020. And so I hope everyone here knows, right? We have had actually a very economical picture of the universe with 70% dark energy, the thing causing the expansion to accelerate, 25% dark matter. We don't know what it is, but we can see it all throughout the universe. We know what it's not. We don't know what it is. And then 5% atoms. And along with this simple picture, one can characterize the dark energy with one more parameter, the equation of state. So the pressure to density ratio. And if dark energy were a cosmological constant, that ratio would be a simple -1, so a vacuum energy. But if nature were more complicated and W wasn't -1, or it changed in some way over cosmic time, then we would know at least the dark energy was much more interesting and much more complicated. So 5 years ago or so, most of the results were kind of consistent with this one. So here's a result. This is from supernova with also data added from the microwave background and some older BAO results, and giving you a measurement or a expected contour around W of -1. And if you expanded that and allowed the equation of state to change over cosmic time, and the typical parameterization people like is a constant plus some time or expansion variable component that goes as 1 minus A, or A is the expansion factor. And in that sort of simple model, the constraints are certainly much worse. The data wasn't good enough to really constrain super tightly 5 years ago in these dimensions, but it was consistent with the expectation, where W0 is -1, WA just 0. And I must say that at the time, I had certain colleagues who asked why I was so interested in continuing to study dark energy and the expansion of the universe, because of course, this simple picture with a high degree of theoretical simplicity was probably right. I definitely heard that from people. Maybe some of you did too. But now, actually 5 years later, the situation is a bit more interesting. If you looked from results from last year from the Dark Energy Survey, looking at a large sample of supernova, combining those supernova, so here this shows the supernova, kind of the distance redshift curve, combining it with information from the microwave background, from an earlier BAO result, and from the weak lensing related studies from dark energy survey. In total, combining all of that gave you these contours, and again in this W0, WA plane. And the interesting thing is that it is not at the simplest lambda CDM point. It was offset at roughly 3 sigma. So that is awfully interesting. And then even more statistically powerful have been the results from DESI. And this, so there was a result last year and then a result earlier this year. And here's just one of the plots from DESI, again showing the results from baryon acoustic oscillation combined with different sets of other information from the microwave background and from a different choice of supernova samples. And that choice makes a little difference, maybe not that much difference, but if you take the combination, one of the combinations, you get results like these, and the errors are now at quite an interesting level. And statistically, it is over 4 sigma away from the simple lambda CDM model, which is, so now you are really at an interesting level. And so the question is to learn more. At the same time, there are 2 other interesting issues in the simple cosmological picture, which maybe you've heard about as well. One goes under the name Hubble tension. This is, I actually took this from the CERN Courier since it was produced kind of not by one of the groups directly involved. But it shows the difference between early measurements of the Hubble parameter with the microwave background versus, let's call them late measurements using stars or using supernova mostly. I think this is the most interesting one here from Shoes. And that difference now is quite statistically significant and has been the attention of a huge amount of work and thought and argument perhaps, but it has certainly not gone away. And it's maybe only become more and more significant. There is yet another possible discrepancy. And this one, occasionally people have called it the sigma 8 tension. Sigma 8 is the strength of the matter-matter power spectrum. This one I think is definitely not in the same category as the Hubble parameter, where the data is maybe more mixed. But what had initially been very interesting, or has been interesting, is that measurements of that parameter, so the strength of the matter-matter power spectrum, 8 is for 8 megaparsecs, varied or was different, let's see, from Planck, so again, early universe, from measurements with weak lensing, late universe. Now, this is a plot from the most recent paper from KIDS. There are 3 galaxy surveys, kind of precursors to Rubin. KIDS, Dark Energy Survey, which I've been a part of, and then a survey with Hypersuprime Cam on the Japanese Subaru telescope. And you can see the DES and HSC results definitely seem lower than this one. This is a new result from KIDS, and it is closer. So maybe that gives raises some questions about whether this is real. There is also a result from DESI showing, you should look at these 2 contours, which have different choices for some of the systematic effects. And the dark energy survey result is in gray. So this is sigma 8 here, omega matter here. That's actually the same contour as shown here. And you can see that the new result from DESI is even further away from the microwave background. So that's interesting too. So this one, I think, there's been more controversy. Whether it's a real tension or not, I think we don't fully know, but it is certainly suggestive. And the fact that, like the Hubble tension, it's an early to late universe difference. And of course, the fact that the observation of differences in the augmented lambda CDM model with W0 and WA also indicate a difference from early to late times, combines to make it, I think, an extremely interesting time for new and additional data on the expansion of the universe and dark energy. So my hope is that, well, I think we are guaranteed to learn something. What we will learn from Rubin, I think only time will tell. So with that, let me just say, and in the time I have left, to say a little bit more about the details of the survey, especially how they're relevant for this sort of cosmological work. So we have actually not quite finalized how we're going to take the images. There has been a huge amount of work in our community towards our observing strategy, and this is a result of the most recent sort of simulated picture of how the 10-year survey would go. And so this shows, in terms of number of visits, so a visit is each time you look in that direction, the wide field, the deep drilling fields, which are shown here, and then the north ecliptic, where you don't have to look quite as often, and then the galaxy, where again, at some point you reach diminishing returns. You don't have to look at it as often. We could also show that, and this is a slightly older simulation, but it has an animated aspect to it, which shows what the course of observing would look like on a couple given nights. One thing you'll notice is that the surveying is not regular. And of course, since we're interested in measuring the distribution of galaxies across the sky, a regular pattern runs the risk of introducing some extra systematic or noise with a strong power spectrum. Having a random or semi-random pattern is much better. So this is the kind of thing we would do from night to night, and we have studied in detail simulations taking into account typical observing, the weather, and what they would yield over 10 years. And lastly, I can show, here are from the most recent simulations, showing the uniformity of the survey after 10 years. So this is in the 6 bands, and the color scale now is magnitude, showing the uniformity of depth over this enormous field of view. And in the mid bands, in this simulation, we get past 26th and even past 27th magnitude in G and R band. And so those are extremely dim objects that we would be seeing across the entire sky. So just to take one closer look, so here's a little cutout from the first look images that I showed in that animation. So this is from the Sloan survey, which is now probably close to 20 years ago. Here's an image of the same part of the sky. It's actually from the DESI Legacy survey, but it's using the dark energy camera and the 4-meter Blanco. Those are our neighbors to us at Rubin. That's actually quite a nice image. But then if you look at our image from first look, you can see even more galaxies. And if you zoom in a little bit further, you can really see. So here's just a tiny little zoom in, and virtually every one of these dots is a galaxy. And of course, that's the amazing thing about doing this sort of imaging. There are a lot of galaxies out there, and there's something to be learned from every one of these little fuzzball galaxies. And if you go back over time, over the past 25 years or so, and look at different papers that studied weak gravitational lensing. So that's the effect where any galaxy you looked at has had its shape and its light affected by the matter, the inhomogeneity of the matter distribution between us and them. And that was first seen in the year 2000 with what are now pretty small galaxy samples of just tens of thousands of galaxies. Here are points for some of the major papers along the way, and our estimate up here at 1 billion to 2 billion galaxies. And that, that's the potential we have for improving the measurements here. It's the size of the amount of sky we're looking at, so it's studying more of the universe, and just the total number of galaxies we'll be able to use. I think I'm probably running out of time. So let me just show what our expectation is for how well we will do. Again, in this W0, WA plane. So this is a set of projections made by the Dark Energy Science Collaboration. So again, W0, WA, just centered at the lambda CDM point, but showing in this in the small contour in the middle what our potential is, combining all of the information that we would get just from Rubin. And so these compare reasonably well with the contours that I already showed. So at these levels, and the central value from the DESI result, we're pretty much guaranteed of seeing something of similar, greater statistical precision even in year one. This is another set of projections from a paper that's in preparation, showing it's guessing how good DESI's third result will be and projecting what we'll see after 3 years with supernova. And again, it's this little contour, which is quite an interesting level. And if you look at the errors here, these are pretty small numbers that would definitely be able to detect the kind of deviations from Lambda CDM. And this is another projection just with cosmic shear, galaxy-galaxy lending, and large-scale structure, so without supernova. And these are interesting levels too. And there's yet another set of projections using strong gravitational lensing systems, which actually will reach also very interesting levels, especially using lensed AGNs and time delays. And I think I've probably run out of my time, so I'm going to conclude by describing what's going to happen going forward. So Steve mentioned that I'm deputy director of the observatory in the construction phase, but I actually get to quit that. That job goes away in 3 weeks, which I realize I should look forward to. So we're declaring an end to the construction and commissioning period next month in October. And we will be able to start the 10-year survey we expect later this calendar year. There are still some aspects of the observatory that need completion. In particular, our dome is not totally finished. And some of that work is going on right now and will continue some into the beginning of 2026 as well. But given all that, we still expect to be able to start the 10-year survey most likely by the end of this calendar year. In addition, and I think maybe I mentioned this, we will start generating the alerts, so the messages that indicate something has changed in the night sky also later this year, as long as we have good templates, so kind of the reference image to use. We expect to release some of the commissioning data that we've taken with the full camera later in 2026, probably the late summer or so of 2026. And then the first data release, and that's when I think we'll have a sample big enough for really groundbreaking work in the kind of cosmology I just was discussing. So it'll be 1 year of data, and will come out 1 year after we finish taking that data, so the end of calendar 2027. And we plan to reanalyze all of our images taken to date on a yearly basis. And so with that, I conclude, and thank you for your attention.
So thanks, Aaron. We have time for some questions. Yeah.
How do you handle satellites, and what fraction of the time do you have to do it?
So the first question is, what do you do about satellites? Well, yes, there are definitely lots of satellites in the night sky these days, with more to come. We've done a lot of study of the impact of Starlink and similar constellations. So our estimate is, with the full Starlink constellation, we would have to mask out 0.5% of pixels. So it's actually not that bad. There would be a significant fraction of images with one satellite streak in them, early or late in the night, and then a smaller fraction in the middle of the night. But at sub%, it's a nuisance and not a major impact. Of course, if there are more satellite constellations, or if they are brighter, significantly brighter than Starlink, then it would be worse. It depends on what goes up. In terms of your second question, how good are the conditions? I mean, this is a very good astronomical site that we're on. So we're on Cerro Pachón. You saw in the movie the image. The Gemini South 8-meter is just down the road, as is the SOAR 4-meter. So it's an established site with a long and well-measured history. It produced, our expectation is that the site should produce excellent images But it's ground-based observing, so you are definitely subject to the weather and local conditions. But we've taken that into account in all of our forecasts.
Yeah, over here.
So, so that's the 0.2 arc seconds that I mentioned. So the information in the images is basically limited by the point spread function that once things are working really well, will be limited by atmospheric turbulence. So spatially, the atmospheric turbulence should dominate, and the residual optical aberrations and the diffusion in the CCDs are subleading. They're significant but subleading. So the very best images that we could get if there's no turbulence are about 0.45 arc seconds. And so even at that level, we would still be Nyquist sampled with pixels at 0.2 arc seconds.
Okay. In terms of your campaign scale of time, what sort of phenomenon, how did you bandwidth-wise characterize the temporal variation of
Oh.
a specific example I may be thinking of is for potentially near-Earth objects to get a good coordinates.
Right, orbit, really.
A good orbit.
Yeah.
What kind of temporal sample?
So we will take second images. We will take 2 images per night in a lot of directions. And so and a lot of that is driven by asteroids that are closer. We really have not optimized for near-Earth objects exactly, but we are sensitive to such things. And actually, you may have heard that there had been a directive from the government to have some project capable of detecting 90% of killer asteroids above some certain size level. And so no existing project has been able to do that, but we actually will be. So.
Any other questions? Yeah, Jerome.
You mentioned in passing that you've learned it's a bad idea to try to take pictures of the moon.
Yeah.
Why is that?
Oh, it trips off the high voltage on our CCDs, the bias voltage. So, actually, you can see it. This bottom image here shows the dome slit open up. So one aspect that's not done is there are giant panels in the orthogonal direction, so that we only have a 11-meter square opening. Those are the first one should get installed Wednesday. But in this configuration, if the moon is straight up, there's nothing you can do. And so we have gotten too close to the moon and has tripped off some of our CCDs. But fortunately, we just turned them right back on and we're fine.
Yeah, up there.
I imagine this is going to do amazing things for gravitational microlensing. Can you speak to that at all?
So, so I think we are sensitive to it in an interesting way. The space-based telescopes will probably be able to do a better job, just because of the scale of the lensing systems with microlensing. Our cadence also is not really optimized for that case, where we're, for much of the sky, we're seeing it only every 3 or 4 nights I mentioned. So, yeah, I guess I want to say that, given some of the things that have come out of ZTF, which have really been, I think, unexpected and very interesting in terms of different sorts of transients, I have an expectation that clever people will find interesting ways to use this data to discover different sorts of transient phenomena. So, people also have asked me, are we expecting to be able to see exoplanets? And I think at first glance, you would think it's kind of hard. Our photometry should be good, especially, when the weather cooperates. But, most of this has happened in space-based instruments. But I would not be surprised if people find clever ways to look for even that phenomenon with our data. So maybe that's a partial answer to your question.
Any additional questions? Okay, let's thank Aaron again. Thanks very much.